Okay, so the idea is to talk about the one-time paired encryption. Let's start with talking about this encryption more generally. This is an encryption that is perfectly secrecy when it's used as it should be, when it is totally random, the key is totally randomly picked, and this encryption can be very, very secure, perfectly secrecy, and it means that even if the one that tries to break this uh, encryption has infinite computing power, even then he won't be able to break this encryption because the idea is that the encryption, the ciphertext, the encrypted text doesn't tell you anything about the plain text. It doesn't help you understand what is the key in any means. For example, if you think of other encryption types, for example, uh, with moving encryption, I mean shifting encryption, if you have one letter, it's not helping, but if you have a text that was encrypted by a shift, by each character was shifted a certain amount of letters, you can use frequency analysis to know which letter in the text came from which letter in the English text. You understand? So the ciphertext, for example, text, the shifting encryption is not perfect secrecy when you have a full text and not just one character. Because you can break it, for example, with frequency analysis, because the ciphertext tells you something. You can do frequency on the, if you see a lot of Q's on the text, you can understand that this Q, for example, is should be in the ciphertext. If there is a lot of Q, you understand Q is not very common in English, so you understand that this Q should be one of the common letters in the plain text in English, for example, E maybe. So it tells you something. But here, in one-time pad encoding, if it is done correctly, namely using a key that is totally random, and not pseudo-random or something like this, truly random key, and the key is of length of the text, which is one of the weak points of this encryption, because let's now work with a key. If you have a text of I don't know how many words, now work with a key that is the length of the text. It's not very practical. So this, you can understand that this encryption, this encoding is very secret, but the problem is it's not practical. The key should be the length of the text, of the plain text, so it can be very long. So what's the idea of one-time pad encoding? The idea is, again, we have a plain text, for example, here low, and we have a key that should be in the length of the text, you see here, and the key should be generated totally, totally randomly. We will convert it to bits. For example, using ASCII, we can convert each letter to its binary representation. Here it's in decimal, but of course you can look at it on its binary representation. And you take the key that you generated, and you are doing XOR between the plain text and the key. For example, you take the 72 and the 88. 88 came from this, and 72 came from here. And you're doing XOR between them, and you get in a number. After doing XOR of two numbers, you're getting another one. Of course, when you are doing the XOR, you convert this to the binary representation of each of 72 and 88, and then doing XOR bitwise between the numbers will give you another result of a number in binary, and then you can convert it to decimal and get this number. You can see that not all these numbers will be translated in ASCII to letters. Okay, that can happen. But here you see we are taking this one and that one from the plain text on from the key and doing XOR between them and getting the number. And we continue each letter by its parallel letter from the key. Again, the key should be the length of the text, the plain text you want to encode, to encrypt. And then we get the results, and this is my ciphertext, namely the text after applying the key on him. So it's unreadable to someone that doesn't have the key. And now how can we decrypt this code? This is the very nice idea of XOR. If you are taking XOR of A, XOR B, so in our case, it's you are taking the plain text and doing XOR with the key, right? Now, if you are doing again XOR with the same key, what you will get, if you take the plain text, doing XOR with key, you will get the ciphertext. But if you again do XOR on the ciphertext, namely you're doing ciphertext, you are doing XOR on it, you're doing XOR on the ciphertext with the key, what you will get the plain text. Because the idea is that A XOR B, and again XOR with B, will give you A. So you can see how we can get again the plain text just by applying the key on the ciphertext. So the one, if I have a text that I want to encrypt, I take the key, encrypt this text, I get the ciphertext, I send it to whoever I want that should have the key in order to decrypt. This, whoever I want that got the text, the ciphertext, want to decrypt the message. So what can he do? He takes this ciphertext and do XOR with the key, with the same key that I encrypted the message. And then he will get again the plain text. And the very important idea of one-time pad encoding is that it's perfect secrecy, because it doesn't tell me if the Oscar, the one that want to do crypto analysis on the ciphertext, look at the ciphertext, it doesn't tell him anything. If I did it correctly, the encoding, it doesn't tell him anything, that ciphertext. He can't break it even with infinite computing power. This is the idea of perfect secrecy. So let's see maybe a total example. So here we have a text, plain text. It's called secret. And we have a key. The key is here it is. Crypto. Again, it's in the length of the text and it's totally random, should be picked. Of course, here it's not really, but this is not a real thing, it's just for an example. So my plain text is secret, my key totally randomly picked, and in the length of the plain text is crypto. Now I use ASCII decimal values for secret and for the key, convert it to binary, and then doing XOR between the plain text, secret, and the key, crypto. Now, doing the XOR between 83 and 75, let's 83 in decimal and 75 in decimal. Oh, let's tell him XOR. Show me how you solve it. And if you look at it, what he does, it converts it to binary. In order to do the XOR between 83 and 75, it converts its decimal number to binary, to its binary representation, for this as well. And then the XOR is bitwise. For example, XOR of 1 and 1 is 0. Remember that XOR is 1 when the numbers are different. For example, 1 and 0 is XOR 1 and 0 is 1, XOR 0 and 1 is 1, but XOR is 0 when the two numbers are the same. For example, XOR of 1 and 1 is 0, and 0 XOR 0 is 0. So 1 and 1 here is 0, 1 and 1 0, 0 0 0, 0 1 is 1, 1 0 1, 0 0 0, and etc etc. So you saw how it did this XOR that it did here. It translated to binary here. It translated to the binary, did XOR bitwise, and got a binary representation, and then converted it back to decimal. So it did XOR this and this, which this is the K, this is the S in ASCII. And now it goes to the next character, doing XOR with this one. Going to the next character, doing XOR with this one. You can see it right over here, the XOR between each letter. And the results, again, the results can be decimal that is not represented in the ASCII, but this is okay. You can pick other letters or something. So this is my ciphertext. I took the plain text, took the key, did XOR between them bitwise, or between each letter, and each letter did it bitwise, and then converted back to decimal and got my ciphertext, which is this one. This is the ciphertext that I send. Now, the ciphertext, which is this one, the one that got the ciphertext and should decrypt the message, take this ciphertext, you see that this one here and this one here is the same, and in order to decrypt, does XOR with the same key, that we encrypted the message. This is the key. Let's do XOR, and what you get from this S, from this E, from this C, and if you look here, it's the same as the plain text that we encrypted. Again, the idea is that if you take A something and you XOR it with B, and then do again XOR with B, you get A. And this is the key idea of this. Here it is. A XOR B is A, and this is the idea. So we did again XOR with the ciphertext and the key, and got again the plain text that we encrypted. And here is the recovered plain text. This is the text that we encrypted. Very, very convenient to use XOR for this, and so this is why it uses XOR. Okay, so if it's totally random, there is the same probability for XOR to give me 0 and 1. Remember that XOR 50%, it has, if you are looking at the truth table of XOR, you will see that half of the result are 0 and half of the result are 1, right? 0, 0 XOR is 0, 1, 1 XOR is 0. So we have two results of 0. 1, 0 is 1, and 0, 1 is 1. So we will have two results that are 1 and two results that are 0. Namely, the XOR operation is very good probabilistics in a sense of security, because if you see the ciphertext and you see zeros and ones, and it came from XOR, you see 1, you see 0, but this is the same probability to get 1 or 0 from XOR, so it doesn't tell you anything. And this is the perfect secrecy. And when you take truly random key, so really the XOR did something that is really 50-50. So it doesn't tell you anything on the plain text. And this is the key idea. If the ciphertext doesn't tell you anything about the plain text, so we can say that it has perfect secrecy. So here in one-time pad, if the key is truly randomly picked and in the length of the plain text, so this one-time pad has a perfect secrecy. But it's not very practical convenient, because think about it. 1, you need truly random key. 2, you need a key that is in the length of the text. Very not convenient. Okay, so we saw how we use the one-time pad, and I won't talk about why it is called that way. I think it's historical reasons. Anyway, this is the one-time pad encoding and its perfect secrecy and how it works and how you encrypt, how you decrypt, and that's it. Thank you very much. If there are any mistakes or correction, please tell me. Thanks for uh, Gemini to do me the examples, so I don't need to write myself. But maybe the last thing, look at the XOR truth table. You will see that the results are 50-50. You see that the results 50% 0, 50% 1. Thank you very much. That's it. If there are any mistakes or correction, please tell me. Thank you very much.